Okay, working out of chapter 3 from our Jesperson text, we'll be focusing on the mole and stoichiometry. So, for this chapter then, we're going to be looking at the mole using Avogadro's number and looking at conversions between molecular and laboratory scales of matter. Basically, we're going to be performing calculations with the mole. So we'll calculate percent compositions, we'll look at empirical formulas and molecular formulas, and of course, we'll perform calculations involving the moles of reactants and products in a reaction. And finally, we're going to look at limiting reagents and the amounts of unreacted substance that might be remaining. And that will lead us into our last topic, which is going to be percent yields, calculate a percent yield. All right, so using a mass to count. So if I have one bun, one beef patty, and 2 pickles, along with some sauce, I can make 1 hamburger. So if I have 100 pounds of buns, 250 pounds of hamburger, 10 pounds of pickles, and 16 pounds of sauce, I'll make 1,000 hamburgers. And so this is the way we can think of the mass, all right, using this with the moles to count. So we have our mole-to-mole relationships. One of these, 2 of these, 1 of these will give us one product. And then that mass relationship, right? So that's what we're going to be looking at in this chapter. So let's define the mole. A number of equal to the number of atoms in exactly 12 grams of carbon-12 atoms. All right, so how many are in 1 mole of carbon-12 then? Well, based on experimental evidence, we know that 1 mole of carbon-12 is equal to 6.022 times 10 to the 23rd atoms of carbon. Now that number is Avogadro's number, right? And so that number then can represent any atoms, molecules, or particles that are in 1 mole. And so a lot of times we'll say 1 mole is equal to 6.022 times 10 to the 23rd. And it's going to be units of X. So we can have moles of X. And so a way to think of the mole is simply treating it as a large dozen. So if I have 3 mole, then I have 3 times 6.022 times 10 to the 23rd units, right? If I have 1 mole of xenon, then I have that many atoms of xenon. So pay attention here because the units for our Avogadro's number will change. It's going to be 1 mole is equal to so many particles. And the particles, again, can be atoms, molecules, or for us, pretty much anything. We can even have moles of electrons, moles of quantum, as we'll see later on. So moles of anything. If we have 1 mole of NO2, then we have 6.022 times 10 to the 23rd molecules of NO2. All right, now we use the mole to go back and forth between molecular and laboratory scale. So we've looked at chemical formulas and reactions at a molecular scale, right? It is known from experiments that electrons, neutrons, and protons have set masses. Atoms then must also have characteristic masses. Okay. Atoms and molecules, of course, are going to be extremely small. And so we're going to need a way to scale that up. We can't just weigh out 4 or 5 atoms, right? They're just too small. And of course, we know that they're 6.022 times 10 to the 23rd. So I don't know if you've ever taken that number and actually looked at the magnitude of that number. But the mole is a really, really, really big number. That means there's a lot of atoms in there. And so for instance, let's see if I can get this pen to come up. If we magnify that out, we have 6.022. And now it's set to the 23rd. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm out of space. 16, 17, 18, 19, 20, 1, 2, and 3. So that's 1, 2, 3. There's thousands. 1, 2, 3. There's millions. 1, 2, 3. Billions. 1, 2, 3. Trillions. 1, 2, 3. Quadrillions. 1, 2, 3. Pentillions. 1, 2, 3. sextillions. So 602 sextillion particles in a mole, right? So it's a really, really, really big number. Now, we're not going to worry about how big of a number it is. What we're going to recognize is that that for us is going to be our conversion factor, right? So we're simply going to turn that into a conversion factor. We're going to put 1 mole over 6.022 times 10 to the 23rd, or we're going to put 6.022 times 10 to the 23rd over 1 mole. So moles of compounds for atoms, we'll look at atomic mass. And of course, we'll get those masses from the periodic table. So if we're going to be converting from moles of atoms to masses, then we're going to use 6.022 times 10 to the 23rd atoms. Okay, so 1 mole of atoms would equal the gram atomic mass on your periodic table. So for instance, if I have 1 mole of helium, then I simply go to the periodic table, and that mass on the periodic table would be the mass of that mole. That mass would have 6.022 times 10 to the 23rd atoms. Now for molecules, we'll have to figure out the molecular mass. And of course, to get the molecular mass, we're simply going to sum up the atomic masses of all the atoms that are in our formula. The mole of a molecule of X will equal what's called the gram molecular mass of X. So we'll look up the molecular mass, and 1 mole would equal that molecular mass, which would also equal 6.022 times 10 to the 23rd molecules. So again, our particle is changing. Now for ionic compounds, the game is the same, right? Except we don't call it a molecular mass, we call it a formula mass. So to figure out a formula mass for an ionic compound, we're still going to get the atomic masses off the periodic table, and we're simply going to sum them up. We can then make the same equations. 1 mole of an ionic compound will have the gram formula mass of that compound, and that will equal 6.022 times 10 to the 23rd formula units. Now you want to be careful here because we could also say ions when we're talking about ionic compounds, and so you got to pay attention to that. One of the little tricks would be to have, let me get back a little bit here, would be to have something like sodium chloride and then ask how many ions are there. And of course, we're going to have 2, 1 sodium, 1 chlorine. Now here you really want to make sure you know your periodic table and your polyatomics, because if I say NaNO3 and then I ask how many ions, remember you're going to have 1 sodium and 1 nitrate. So that's going to act, that polyatomic acts as a single ion. So it's can get a little tricky in there. You really have to know your definitions and pay attention to what's being asked. All right, in general, we call this the molar mass. So typically we won't say formula mass or molecular mass or atomic mass. We'll simply say molar mass. And that way I'm encompassing all the possibilities here. In general, the molar mass would be 1 mole of X is equal to the molar mass of X, which would then have 6.022 times 10 to the 23rd formula units, right? All right, so the SI unit for the amount is the mole. So the mole is an SI unit. 1 mole of substance of X is equal to the gram molar mass of X. This is like the 3rd time we're saying it, so hopefully you're catching on. This is the important piece you got to bring home. Most of you might already know this because most of you have had a general chem of some sort. And so this is not your first time dealing with the mole, but so hopefully we're just knocking off some cobwebs here. So using our periodic table, then we know that 1 mole of sulfur would be equal to 32.06 grams of sulfur. If I add the NO2, 1 mole of that would be 46.01 grams. And for that, we got the molar masses from the periodic table and summed them up. Here we can also make conversion factors, right? And we can relate now the mole to a mass or the mole to a particle. Okay. Again, Avogadro's number will be our conversion factor, as well as the periodic table. Okay. All right. So what is the molar mass of C2H5COOH? So we've looked a little bit at organic. We didn't get into a whole lot of depth there. The C2H5 is going to be an ethyl piece, and the COOH is an acid. So this is actually acetic acid. Now, it really doesn't matter what it is, whether it's organic or not. Again, what we're going to do is we're going to go to our periodic table. We're going to find those elements, get the mass from our periodic table, and simply sum them up. And that sum will be A, B, C, D, or E. And I'll give you a chance to figure that out. And hopefully, once you've done the calculation, you know that it's going to be 74 grams per mole. So the way we did it, well, we have 3 moles of carbon, right? Because we have 2 here, but we also had 1 there. We're going to multiply that by the periodic table number of 12.0. I usually use 12.01, but our textbook is using just 12.0. We have 6 moles of hydrogen. Again, we have 5 here, plus the 1 over here gives us the 6, plus 2 moles of oxygen, because we have 2 O's. And when we multiply all that out and sum it, we get the 74 grams per 1 mole. You can see all of our moles cancel out, and voila. All right, what is the formula mass of magnesium phosphate? Magnesium phosphate. All right, hopefully you came up with 262.9. The biggest key here is you have to know the formula based on the name. And so if you know the formula, then you can easily do the calculation. So hopefully you come up with the formula as Mg3PO42, right? Magnesium we know is in group 2A, so that's a +2 charge. Phosphate, ATE tells us it's going to come from our polyatomic list, so it's going to be PO4. And we can also look up that it's a -3 charge, and then when we crisscross that, we'll have 3 magnesiums and 2 phosphates. After that, we'll go through the same process where we have 3 moles of magnesium, periodic table value is 24.3, 2 moles of phosphorus, don't forget this subscript 2 here on the outside of the parenthesis multiplies by the understood 1, also by the 4 to give us our 8 oxygens. We then multiply all that out, so our moles will cancel out here, here, and here. We end up with moles of magnesium phosphate at 262.9. All right, so learning check using your molar mass. How many moles of iron are in 15.34 grams of iron? So again, we can think of these things as just simply conversion factors. So what do we want to determine? Well, what we're actually looking for is how many moles of iron have this mass? So what is it that we know? Well, if we go to our periodic table, we know that 1 mole of iron is equal to 55.85 grams. So we know where we're starting and we know where we want to get to. So what we can do then is just set up our ratio so that we get what we want on top and eliminate what's been given on the bottom. So for instance, we'll take that 15.34 grams of iron that we started with. We want grams of iron on the bottom, 1 mole of iron on the top. We can see the grams of iron will cancel out. Our answer will be left in mole. And then again, we want to make sure we're applying significant figures here as well. All right. If we need 0.168 moles of calcium phosphate for an experiment, how many grams do we need to weigh out? Well, here we want to determine what? Right, now we want the mass of the calcium phosphate. We're going to start with moles. So typically what we can do is think of this as being it's always going to be a conversion, but everything's going to center around the mole. So if you go under student resources on D2L, there is a mole calculation sheet there. It gives you a little flow chart. A lot of times we know what to do, we just don't know when we need to do what, and when the questions start getting complex. And so here, we can think about where we want to start. We're starting at mole. We want to get to mass. And if I look on that flow chart, it's going to tell me what to do. It's going to tell me that I'm going to need to calculate the molar mass of the calcium phosphate and then multiply that by the number of moles. So first we'll get the molar mass, and that works out to be 310.18. Now, using that, I'm going to set up my equation. This time I want mass to be in the answer, and I want moles to be eliminated. So I'm going to put moles in the bottom so it can cancel out with the question. It's going to leave me with a mass, and that mass is going to be 52.11 grams. Again, you can get that mole flow chart off of the D2L if you'd like. Maybe that'll help you out with that. All right, how many moles of CO2 are there in 10 grams? And I'll give you a pause here. You might have to work this problem out first. Then once you push play, it's going to be 0.227. So the molar mass of CO2 then, we can sum that up to be 44.01 grams. And now I'm going to take that 10 grams, I'm going to divide by the mass on the periodic table. That way my answer will be in moles. I can see the grams cancel out, and that's going to give me 0.227 moles. How many grams of platinum are in 0.475 moles of platinum? Give you the pause. All right, hopefully you selected E. The molar mass of platinum was 195.08 coming from the periodic table. I want moles to cancel out, so I'll put 1 mole on the bottom. I'll put the mass on the top. Moles then will cancel, and we'll be left with 92.7 grams. So again, using moles in calculations, we have the grams of the substance of A. Using that molar mass, we can get moles of A. Then using Avogadro's number, we can go between the units of A. So we can go through particles to moles, and then moles to mass. Now moles are always going to be the central. In fact, if you pull that flow chart off, then you can see I've got it reversed. So that I put mass at the bottom, particles at the top. That doesn't matter. It's a flow chart just to help us with the calculation. But what you also notice about mine is I've given you the wings on the left and right. And there we can see that we're going to have a solution base, which we'll be seeing in the next chapter. Eventually we'll also have a gas base, which we'll be looking at further down the road. No matter what though, you're always going to be centralized around that mole. The mole is the center of everything we do in chemistry. So if I'm starting with mass versus the units, I just need to use either the molar mass or I'll need to use Avogadro's number. Okay, so it's always going to be one of the two. Now, if I want to go from mass all the way to the units, or if I want to go from the units to the mass, it's got to be a two-step process where I'm going to have to go through the periodic table and take advantage of that mole relationship. So, how many silver atoms, there's our particle, are in 85 grams of a silver bracelet? Well, what do we want to determine? Well, this time we're going to go from mass to atoms. So, what is it that we know? Well, we can go to our periodic table. We can find the mass. We also know we have a relationship with particles to the mole. So now what we're going to do is a two-step problem. We're going to go from mass to mole and then mole to atoms. So I'm going to set that up like this. I'm going to start with my 85 grams. That's a mass. So I'm going to put my mass from my periodic table on the bottom. I'm going to put my mole on top. That's going to let me cancel those out. Next, I'm going to put my mole on the bottom and put my particles on top. Now my moles are going to be canceling out, and I'll be left with the particle I'm looking for, atoms. So here I'm going to multiply 85 by 1, divide by 107. Then I'm going to multiply that by 6.022, divide that by 1, and then I'll carry that 10 to the 23rd outside of that. So sometimes, once I have this number, I might have to make some adjustments to this. Now, if you're using your calculators for this and you have your exponents set up on your calculator, which I'm sure some of you do, it'll take care of all that for you. All right, so what is the mass in grams of one molecule of octane? So C8H18. So here, we're going to go molecules of octane to moles of octane to grams of octane. So the first thing we'll do is calculate the molar mass of the octane. I have 8 carbons, which is 96.08 grams. I have 18 hydrogens at 18.14 grams. Summing that up, I get 114.22 grams of octane. So the next thing I'm going to do is convert one molecule of octane into grams. So 114 grams of octane per 1 mole times 1 mole of octane over the molecules. Moles of octane will cancel out. I now have a relationship between mass and molecules. So 1.897 times 10 to the negative 22 grams for each molecule of octane. All right. Calculate the number of formula units of sodium carbonate in 1.29 moles of sodium carbonate. Again, the game mathematically is the same, except now we're using an ionic compound instead of a molecular one or an atomic one. It's no big deal. We're going to take 1.29 moles, we're going to cancel those moles out, and we're going to make it 6.022 times 10 to the 23rd, and now it's going to be formula units instead of atoms. That works out to be 7.77 times 10 to the 23rd particles of sodium carbonate. How many moles of sodium carbonate are there in 1.15 times 10 to the 5 formula units of sodium carbonate? So again, we'll start with what we're given, 1.15 times 10 to the 5, and we'll divide that now by the number of particles. That way our formula units will cancel out, and we'll be left in moles. And that's going to be 1.91 times 10 to the negative 19 moles. All right. How many atoms are in 1 times 10 to the negative 9 grams of uranium? The molar mass of uranium is equal to 238.03 grams per mole. Here are your options. So give you a moment to work that out, i.e. a pause. And hopefully you came out with C. So you're going to start with that 1.00 times 10 to the negative 9 grams. We're going to use the molar mass to get moles of uranium, and then we're going to use Avogadro's number to get the atoms. Grams will cancel out, moles will cancel out, and so our unit will be atoms. And we get 2.53 times 10 to the 12. How much in grams do 8.85 times 10 to the 24 atoms of zinc weigh? And there are your options. All right, so here we get 961 as our answer. We're going to take that 885 times 10 to the 24th atoms, so we're in particles. I want to get particles to cancel out, so I'm going to put 1 mole on the top, Avogadro's number on the bottom. That would give me moles at this point, but it says how much in grams. And so then we're going to use that periodic table, get the molar mass. The mass will go on top. That way the moles can cancel out. And that'll give us 961. All right, last problem. Calculate the mass in grams of iron 3 chloride in 1.53 times 10 to the 23rd formula units. All right. Hopefully you came up with 41.2. And once again, we see we're going to take our formula units. We're going to get those units to cancel out. Moles will be on top here. Then we'll get moles to cancel out, and we'll have mass on top there. So formula units will cancel, moles will cancel, we'll be left with mass. And that's how we got the 41.2 grams. All right, so that was our mole to mass and mole to particle, and thus particle to mass and mass to particle calculations. Next, we're going to turn our attention to mole conversions. So stay tuned for segment 2, and there we'll look at how we're going to deal with mole to mole and changing A into B. All right, stay tuned.